Hello and welcome back to Physics Tutoring for Mods. In this video, we'll be going over velocity time graphs and what the slopes of those graphs as well as the area under those graphs represent. Because they mean two different things and they tie into position time graphs. So if you haven't checked out my video on that, be sure to, because you're going to need that knowledge for this. The area under a velocity time graph is going to be the displacement of that object. Suppose I had a velocity time graph, which is similar to a position time graph, right? It's just velocity over the time. How much is the velocity changing over time? Velocity is equal to 5 meters per second. Since velocity would go on the y-axis, this would be a horizontal line. Okay? And then since time goes on the x-axis, this time would be on the x-axis. It would just be a point here. Suppose I said a car traveled at 5 meters per second for 4 seconds. How far did the car travel? That's just going to be 5 meters per second times 4 seconds. Give me 20 meters. That's our displacement. Now, why is that? Why is it that the area under a velocity time graph represents displacement? The meter per second times seconds cancel out to make only meters. And since we know that velocity is displacement over time, the area under this graph will give us displacement, not distance, because displacement can be negative. And we can have a graph that looks like this, right? It goes down, and the area under the graph would be negative. But we can't have a negative distance. That's why the area under this graph would be displacement. Makes sense, right? Meter per second times second. Or if you said 60 miles an hour, I'm going 60 miles an hour. Then in 1 hour, how many miles would you go? You just go 60 miles, right? Or in 2 hours, you'd go 120 miles. Very similar to that. But that's the first case. Just a plain line and a rectangle underneath it. But now, what if we have a trapezoid? How would we calculate the area of this trapezoid? That looks like this. The velocity looks to be changing, so it starts at 2 meters per second. And it slowly increases, which means the object is getting faster and faster till it reaches 14. How do I calculate the area under this graph? First, I look at this, okay? I shade in all the area around it, below it. So I just go like this. And then I try to divide this area into a rectangle and a triangle. So I cut over here. And this area is a rectangle, and then this area is a triangle. So I can find the area of those separately and then calculate it, the displacement. Or you could just use trapezoids, but I find this method more easy and more useful in tests. So I'm just going to go over this one. Let's just say this point is 6 seconds, and then this, they already gave us, right? 2 meters per second. And over here, it's 14 meters per second. So the area of the rectangle is going to be length times width. Width is 6 seconds times length is 2 meters per second. Displacement here is 12 meters, but that's only one part of the area. What about the triangle? That's going to be 1/2 times, what's the width? 6 seconds times, what's the height? You might be tempted to say 14 meters per second. I once did those mistakes myself. But you have to remember that the height of the triangle is not how high up it is from the ground, because 14 is this much. But the triangle is actually only this high, right? This is the height of the triangle. If I was to highlight this in a different color, this is the height, not this. So how do I get the height of the triangle? I subtract this base thing, the base velocity, 14 minus 2, and then I get the height of the triangle. Because I'm starting here, I'm subtracting this extra stuff. I'm left with 12 meters per second. 1/2 times 12 meters per second times 6 seconds. Seconds cancel out. 3 times 12 meters is 36 meters, which you can see here. And then you have to remember, you have to add the total area, right? So 36 meters plus 12 meters is going to become 48 meters. That's your total displacement. And always remember to say displacement, okay? Not distance. The question is, though, what if you have a velocity graph that goes below the x-axis, that its slope is negative and it goes below the x-axis, right, like this? How do you calculate the area of this half? Well, we can split it into two triangles, right? This triangle and this triangle. But is this triangle going to be negative or positive? It's going to be negative. And here's why. First off, I'll give you two explanations for it. First off, if you're calculating the area of this triangle, it would be 1/2 times this positive x value, right? This positive x distance from this crossing point. Not the total x distance, it's just the x distance from this crossing point. So I would just say x cross times what? Negative y. Because this is negative, right? That y is negative here. It's not positive height. It has a negative height. It's going to be times negative y. And then you get a negative 1/2 xy, or a negative displacement. That's why the area here would be negative. And another explanation for that is, if you think about what velocity actually means, right? It's how fast you're going. You can either go in this direction or this direction. And then you have a magnitude. How far are you going in that direction? So what this graph represents is, I started off with a high speed in this direction, but then I slowly reduced that speed, because you see how my speed is reducing, right? Slowly reduced it. And then if I should continue this here, slowly reduced it, and then it hit 0. So then I didn't do anything. But then I started going backward. So then my arrow started turning from small backward to large backward to large backward. So I'm speeding up in the backwards direction. Okay? So it makes sense that if you're going backward, your displacement would be negative, right? Because you're going in the opposite direction. So your displacement would be in the opposite direction of the positive direction. So you get a negative displacement here. And you just add these, okay? How would you get the total displacement? You just add this. How much did it go in the positive direction, or the positive displacement, plus the negative displacement, or how much did it go in the negative direction? Okay, so positive area or positive direction displacement plus the negative displacement, which is this. Now, net displacement or total displacement is a signed sum, which means plus or minus, right? Then area can have a negative value. But over here for total distance, you see that it doesn't. Why is that? Because you remember how total distance was the total amount you travel. Direction doesn't matter, so you can't have a negative, right? Because distance is just how far did you travel. So in that case, I would just add the total values of both of these, right? Just the absolute values of both of these. I don't need a negative because I don't have a negative distance. I only have how did you travel, how much did you travel. That's it. So I would just add the absolute value of the positive area and then the absolute value of the negative area. That's the difference between these two things. Be sure to keep that in mind. So now, let's go over some problems, right? More detailed problems are going to be on website, artslearning.com. But for now, let's just go over some basic ones. V is equal to 6 meters per second. So it's going to be like that, a line, right? 6 meters per second, straight line. From t equals 0 to t equals 5 seconds. So 0 and 5 seconds. And then you create an area under this. What's the magnitude of this area? Well, it's pretty simple, right? The length is 6 meters per second because that's how high up it is, right? And the width is 5 seconds because that's how far it is. What's the width is on the x direction? You get 30 meters. That's your displacement. Velocity rises from 3 meters per second to 11 meters per second over 4 seconds under constant acceleration. Find the displacement with the rectangle plus triangle method. Okay, so we start off over here, okay, at 3. We slowly rise to 11. We stay at 11. And then this entire thing happens in meter per second for these units. And it all happens over 4 seconds. So it might not look like it directly matches up, but imagine it matches up, okay? For the sake of my drawing. And as always, we can split this into 2 areas. This area and this area. So let me calculate the area of the rectangle first, right? That's going to be 4 seconds times 3 meters per second, because this is the base height, right? It's this height this graph starts at. That gives me 12 meters. Seconds cancel out. Now, what about the area of this triangle? That's going to be 1/2 times, well, it still goes over 4 seconds, right? The width is still 4 seconds. But remember, the height is the height of the triangle, not the total height. So it's going to be 11 minus 3 meters per second, which is going to give you 2 seconds. The seconds cancel out. 2 times 11 minus 3, 16 meters. So the total displacement would be, or this total displacement is equal to 16 meters plus 12 meters in the positive direction, so 28 meters. Pretty neat. Now let's try and find the area under a negative slope velocity graph. So try it by yourself first. I want you to pause the video and give this a try, because this is the most important concept in this video. All right, let's give it a try. You start from 4 meters per second and you go down to negative 2 meters per second. All of that over 6 seconds. So you end at 6 seconds. Find the net displacement and the distance total traveled. They will differ. So first I have to find this marking point, right? Because I need to find this negative area and this positive area. But I can't know that unless I find where this is, because then the width of this triangle is going to be this length, right? And the width of this triangle is going to be 6 seconds minus this length. So I have to calculate the slope of this graph and make it into a graph. Y is equal to, so let me find the slope of it, right? 4, 0, 6, negative 2. Negative 2 minus, 0, 4. Right, negative 2 minus 4. This is in meter per second. Over 6 minus 0 seconds. So this gives you negative 1. Okay, negative 1x plus, well, the y-intercept over here is 4. So this would be your line if it is just a regular line, not a velocity time graph. What's the x-intercept for this? Well, you just set this equal to 0. 0 is equal to negative 1x plus 4. Negative x is equal to negative 4. X is equal to 4. Pretty neat. So I know that's where I stop. Now to calculate the area of both of these. The blue one, which I'm going to do on the left here, is going to be 1/2 times, we know we go till 4, right? So the blue one's thing, the blue one's x value, goes till 4. It's the width is till 4. Times 4 seconds, because it's in seconds. And then what's the height? Again, 4 meters per second. Seconds cancel out. Becomes 8 meters. Over here, what's this negative area going to be? Which I'm going to do in red. 1/2 times, well, we know the height is negative 2 meters per second. And then what is this x value? Or what is this width here? That's going to be 6 seconds minus 4 seconds, right? Because this width is this total width, or total s value, minus this stopper here, the cross point for 0. So it's going to be 2 seconds. Seconds cancel out. -1 times 2, -2 meters. So my displacement total would be 8 meters minus 2 meters, right? Because this would be a negative area, which gives me 6 meters. And as for my distance total, d tot, that's going to be the absolute value of both of these added, right? So absolute value of 8 meters is just 8 meters. Absolute value of -2 meters is positive 2 meters. So I end up with plus 10 is equal to 10 meters. That's it. Now let's go over the slopes of velocity time graph, which is going to be equal to acceleration. So if you think about it, the slope of velocity time graph, well, delta v is going to be in what units? Well, 2 meters per second minus 1 meter per second, or any meter per second minus any meter per second. Units are just going to be meter per second. And delta t, what are the units for that? That's just seconds, right? 4 seconds minus 2 seconds is just seconds. What is meter per second divided by second? That's just going to be meter per second squared. Okay, because the s becomes m over s times 1 over s equal to m over s squared. And if you know your SI unit, you know this is the unit for acceleration. Okay, acceleration. Now, you know that the slope of a velocity time graph is acceleration. So a negative slope would mean negative acceleration, and a positive slope would mean positive acceleration. Acceleration means how fast the velocity is changing. Okay? So you could have a positive velocity. Suppose your car is traveling positive at a positive speed, okay? Or positive velocity. But then you're hitting the brakes. So you're going to be accelerating backward because you're stopping the velocity. You're changing the velocity, right? Anytime you have a change in velocity, you have acceleration. So if you're changing the velocity, then you're going to be hitting the acceleration in the opposite direction of velocity. Velocity is going to be forward. Acceleration is going to be backward, which makes the car stop. If you hit the accelerator, then both velocity and acceleration would be in the same direction, which would give you an extra push this way, because you're going to keep increasing your speed in the positive x direction, and you're going to keep going faster and faster. Okay? So that's all you need to know for regarding this. Now, more about its calculations and derivations. As we know, right? Since velocity's rate of change means delta v over delta t, that's what acceleration measures. So A average, which is just acceleration average, okay? That's going to be the conventional, what you're going to hear written. It's just going to be VF minus VI over TF minus TI. And if you know what HF and HI were from my previous position time graphs, you know that this means velocity final minus velocity initial and time final minus time initial. The units, meter per second squared. So in this case, right, if you just look at the final velocity, 26, you subtract 8 from it because that's the initial velocity in meter per second, and then you would see how many seconds it took. Let's just say it took 6, right, because each of these is scaled by 1. 6 seconds. Divided by 6 seconds, you get 3 meter per second squared. That's your positive acceleration. And remember, if acceleration and velocity are in the same direction, the object will speed up. If acceleration, so if I do this acceleration vector in blue, same direction, it speed up. If acceleration was in the opposite direction, the object would slow down, right? Because you're conceding. The acceleration is making the object slow down. Now, these are a few graphs that you could see, okay? Graphs look like this. Rectangular, instant time-changing graphs. Okay? Now, this is obviously not very realistic, right? Because acceleration can't change that fast. Velocity can't change that fast. But it's a rough scale or a rough estimate to what real graphs could look like. Imagine you start with acceleration 3, right? This is an acceleration time graph, which is the same as velocity time graphs, really. You start with that, and then you go a is equal to -2. So similarly, the area under an acceleration time graph, area, right, is going to be velocity. So there's 4 things you need to know, right? Slope of position time graph is velocity. And slope of velocity time graph is acceleration. And area of velocity time graph is displacement. Displacement. Okay? Those are the 4 kinematic basic equations you need to know. The others, is like projectile motion, we'll be going over later, and the more difficult ones. But these are the more basic concepts you need to know. Okay? So in this course, we'll be dealing with only constant acceleration, because this isn't calculus-based physics, it's algebra-based physics. If you want to look at more calculus-based physics or something of that sort, then you can check out other videos. Or I'll be sending out a course soon on that as well, so you could look at that. So let's read acceleration of the slope of velocity time graph. So a velocity time graph passes through 2 seconds, 5 meters per second, and 8 seconds, 23 meters per second. Compute the acceleration. Pretty straightforward, just compute it. 8 seconds minus 2 seconds. This is 18 meters per second over 6 seconds, or 3 meters per second squared. Okay? From an AT segment, one rectangular segment shows acceleration is equal to 4 meters per second squared from t equals 0 to t equals 5 seconds. Start at VI equals 2 meters per second. Determine the velocity at the end of the segment. Okay, this is something important you need to know. The change in acceleration or the change in velocity is the area under the acceleration time graph, right? Because meter per second squared times second is meter per second. That's why the area under acceleration time graph is velocity. So, whoops. Okay. Now, let's continue. 4 meters per second squared times 5 seconds. Seconds cancel out, but you're still left with 1 second. So delta V is going to be 20 meters per second. But this is delta V. What's initial V? 2 meters per second. So acceleration is in the same direction as velocity, because velocity is positive and acceleration is positive, which means you're going to add both of these. So you're just going to get 2 plus 20, or 22 meters per second. So that means you changed 20 meters per second with a 5 meters per second squared acceleration. Pretty straightforward. A VT graph is steeper in its first half than its second half. Okay, so probably something that looks like this. Or, yeah, it keeps going. It's not flat. It might look a bit flat, but it's steep in the first half, but in the second half, it's more broad. Is the acceleration constant across the whole graph? Well, definitely not, right? Over here, the acceleration is a slope. So you'll have a steep slope, right? So a high slope. or a high acceleration. Here, the acceleration is slower because you have a lower slope or a more broad slope. So you wouldn't have a constant acceleration. And then the last thing I wanted to impart on you guys would be the difference between graphs and how a velocity time graph will look, how you'd sketch it. Okay? What I mean by that is, if your position time graph look like this, linear, your velocity time graph would look like this because you'd have a constant slope, right? The slope of the position time graph is velocity. And since you have a constant slope, you'll have a constant velocity. And then the velocity and the acceleration would just be 0 because the slope of the velocity time graph is 0. If your position time graph looked like this, like a quadratic, the velocity time graph would look like this because the slope is increasing, right? You can have, this is a more calculus topic, but it's just good to know, right? You start here, so you have a small slope, you're slowly increasing, right? If you mega zoom in into this area, you're only increasing by a bit. You're not increasing as fast as you are on the other sectors of that area. So here you're increasing faster. Here you're increasing faster. You can see it visually as well, right? 1 squared is equal to 1. Y is equal to x squared. 2 squared is equal to 4. 3 squared is equal to 9. You see how faster you're increasing? From here to here, you're increasing 3. Here to here, you're increasing 5. So you're increasing way faster, right? So the velocity time graph will look linear, which means the acceleration time graph would have a constant value like this. Because your acceleration is the slope of velocity. Velocity would have a constant slope, like 2 or 3. So acceleration would be down here. At that rate. So that's all you need to know. And you could deal with the scenarios where it's like x cubed and it's not just x squared, but that's more calculus-based physics. We'll get to that later on, okay? You don't need to worry yourself with it right now. And make sure you review those concepts, the acceleration, slope, area, all that, how the slope under acceleration time graph is changing velocity, and you should be good for this unit. See you guys next time when we're covering the big 5 kinematic equations.